to see how I wrote it up. That's one of the hardest things about analysis, is a proof never looks like the steps someone did to figure it out. Because there's all this crap computation you just have to get through. But okay, so anyway, star is less than b minus a times, well, this looks like b to the n minus 1. This looks like b to the n minus 1. This looks like b to the n minus 1. And I think you guys get it. But a lot of b to the n minus 1s. Yep. How many? N of them. You can, if you don't believe me, just well, just count. There's n minus 1, and then it goes from power n minus 1 to 0. How many numbers are there? N minus 1, n minus 2, blah, blah, n of them. Does that make sense? So this is n times, which is just equal to b minus a times n, b to the n minus 1. Yeah? Again, it looks scary, not really that scary when you just sit down and break down the steps. And even figuring it out was not that hard. Right? The only thing we had to use is that a was less than b. And we instantaneously got everything. All right, cool. So yesterday I didn't state this lemma because yesterday I was going to do it differently. But on the way to school today I decided, you know what? I'm just going to state a fourth lemma that basically breaks down the last step of the theorem and then just say the theorem's a consequence of these in this order. So the last lemma I want to state, and this is kind of a nice way to put it. So if you guys want a little like homework for tonight, a good thing you guys can do tonight is make sure your notes are nice, grab them, sit down with Rudin, and see how these lemmas appear in his proof. Okay? But okay, so lemma 4 it simply says this. Let x be an r. And then we'll also let t be an r, or sorry, x probably positive. T be an r also positive, such that t to the n is less than x. So I'm taking the thing that I will eventually try to find an nth root for, and I'm taking someone whose nth power is less than it. Can you guys see this back there? All right, I can move it to another board, I think. How about this? Yeah, I'll do that. Let me put it over here. Because this is my last proof, and then the proof of the theorem should be very easy. But so lemma 4. Oh yeah, if you guys ever, for some reason, build a university, don't put like unmovable desks in front of the board. But yeah, there was a question too. I'm sorry, I skipped over it. Someone was raising their hand. Yeah.
What were you assuming about n?
What?
What were you assuming about n?
So same conditions. N is positive. But okay. So again, let x be a real number and t that's positive, and t be a real number that's also positive, such that fine. If you want n, we'll just say n is a natural number, such that t to the n is less than x. So here's the actual thing. I'm going to put in parentheses t to the n is greater than x. Because I'm actually going to be proving two lemmas simultaneously, but I'm just going to prove one of them. The other one follows very similar. You can find it in the book. But then there exists, let's say S in R, also positive. And S in R, maybe I'll put it better, S greater than T in fact, such that S to the n is also less than x. So what I'm saying is if I find, if I'm given a benchmark and then I'll put in parentheses, sorry, S to the n, so I should be careful. S greater than T in the parentheses version of this, S less than T. And in this version of it, S to the n greater than x. So let me just state the non-parentheses version and I'll state the parentheses version next. What I'm saying is if I have an x that I'm sort of aiming to try to get to, if I find something whose nth power is less than it, I can find something slightly bigger whose nth power is still less than it. Does that make sense? That seems very reasonable when you think of it that way. And in the other version, just saying if I find something whose nth power is greater than it, I can find something whose nth power is slightly smaller, whose nth power is still greater than it. Okay, and this I'm going to actually have to use my notes because I worked out how it works. But no, I don't want this page. I want the next page. Here. Okay, so I'm just going to prove the first half, the non-parentheses version. I'll tell you. So I'll tell you how it works in the parentheses version if you want. I mean, it's not too bad. But again, And this makes sense, and you'll see how this fits into this proof. But this is a very reasonable thing to prove. When you think of just this fact, this is a very reasonable thing to prove. Right? This is something that, in fact, you all kind of think that's obvious. But you're wondering how this proof's going to go. So, so assume t to the n is less than x. So here's the thing. Okay, if n equals, this is not going to be an induction only because it's going to be a nightmare to try to do with induction. But you can tell at least that the first case, t equals or n equals 1 is obvious. Sure? How would you do it? That's my first question. How would you prove it to me if n was 1? So I'm asking you, if I have a t such that t is less than x, there's something bigger than t where s is less than x.
X plus t divided by 2.
Sure, you could take the midpoint. You could average x and t. X plus t divided by 2. Good answer. How about using a theorem I proved yesterday? What was that? Not the reals. The rationals are dense. Remember, we proved yesterday between any two reals there exists a rational. I could, if this was n equals 1, I could just say, well, there exists a rational number between them. We proved it yesterday. There's another proof. But yeah, both work. The midpoint's a good idea too. I like it. Okay, cool. But now this is not so easy. So what I'm going to try to do, so here's the idea. I know how big t is roughly. I'm going to try to find something slightly bigger. So what I'm going to really do is, so the idea, so find h such that t plus h to the n is still less than x. Does that make sense? Find a little number that's a function of t, right? Because I can't just pick anything. I can't make h 1, right? Because if I make t really, really close, that 1 would push it over. So I need to find an h that is going to work. And I'm not going to actually go through how to derive it because, again, this is one of those things that when you know that I want to use this inequality, it's sort of obvious. But since you guys don't know that, and you have to think about it, but the h I'm going to use is just this. Where did I write that? So I'm going to choose h to be strictly less than the following thing. Where did I put it? It should be up here. Oh, here it is. Okay. X minus t to the n over n t plus 1 to the n minus 1. Yeah, again, not like the most obvious thing. Again, this is one of those things you sit down and think about and it works out. All right? So here we go. I'm going to prove to you this works. So again, instead of, so I'm going to try to take advantage. And I mean, can you guys see why this might be what we want? Is if you look at the inequality we proved. That looks like part of the inequality we proved. You see that? All right, cool. So instead of showing you, so what I'm going to do is I'm now going to show you that t plus h to the n minus t to the n is very small. So now I'm just assuming pick any h smaller than this. So maybe I should put the word pick. But pick h smaller than this, and then it should work. And again, it's very important, it depends on t, right? Because again, if t is very close to the nth root of this thing that you guys know it already exists, it's got to be a very small number of adding. So this thing here is less than or equal to. Now this is my lemma 3. So this looks like my A, this looks like my B. Or sorry, this looks like my A, this looks like my B. So it looks like t plus h minus t times n times, what am I missing? T plus h to the n minus 1. Right, and this is my lemma 3. Simple enough? Because yeah, again, this is my B, this is my A. So then we just proceed. Well, what's this thing in the parentheses? This is just h, and this looks like n t plus h to the n minus 1. Yep. Well, now what should I do?